With all the hype surrounding Tesla's full self-driving Beta 12 and Elon Musk and Ashok Elluswamy's drive around Palo Alto a couple of Fridays ago, I've sensed a growing confusion about exactly what it means to have end-to-end neural network processing and how it's different from what we've had in the past. So that's what we're going to take a look at today. Hey y'all, it's Dr. Know-It-All. So today I'm going to stay at a fairly high level about all of this stuff. I actually want to do a video soon about diffusion models versus transformers versus convolutional neural networks, because in particular, Elon Musk has hinted that Tesla's full self-driving team is using other methodologies besides transformers to do what they're doing right now. And there are efficiencies for that. But today I want to keep things at a relatively high level and just talk about the three main parts of self-driving. And that is perception, decision-making, and output controls. So of course, the primary exemplar of self-driving is us human beings, right? Because we do self-driving all the time. And so perception is our eyes, and to a lesser extent, but importantly, our ears as well, because we do hear things like sirens and stuff like that. And of course, our inner ears that have balance, so that as you're going around a corner, you can feel whether you've got a lot of G's that you're pulling. Of course, you also know because you've turned the steering wheel a lot as well. But basically, if you're like, oh, I'm going around really fast and I'm in a very tippy car, or I have old tires that might slip, or it's raining, or it's icy, right? So you need that extra sense to be able to know the kind of G's that you're pulling in centrifugal force as you're going around, or if you're accelerating or something, right? How far back your head is being pushed into the seat behind you, or if you're braking, et cetera, et cetera. So anyway, you do need other things besides vision, but vision is the primary mode of driving for human beings. Then the decision-making process comes in, and of course that's our brains, and our brains are sitting there going like, okay, what do I need to do to stay safe? And what do I need to do to get to my destination as efficiently as possible? So there's kind of short-term planning, which is just don't get in an accident. And there's longer-term planning, which is like, how do I navigate to where I want to go? And of course, I'm assuming you're not using your phone and you're not using GPS and stuff like that. You're doing this either from memory or just because somebody told you to go to that place. And so you're trying to find it. And then of course, the final step is the control output, or what you do with your hands to turn the steering wheel, or what you do with your foot to press the brake or press the accelerator. And of course, to be clear, in a human car system, we're actually looking at something more like Optimus driving a traditional car, right? So you're looking at a robot that has to make a lot of interesting decisions with all of its actuators or human muscles or something in order to make very, very simple outputs to the car. So we get to abstract that out in a self-driving car because it can directly turn the wheel or press the accelerator or the brake. So you don't have to worry about having a human being and controlling all of that. But everything I'm talking about today is going to transfer to Optimus directly. So just understand that the control output is much more complicated in a humanoid type robot, but it's the same basic idea. All right, so let's turn from humans to robots or computers, whatever you want to call it. If we look at the input vision system, in other words, the input space, you can look back over time, the early versions of machine learning, artificial intelligence that were done. There were attempts made in the 80s and 90s and even previous to that, but what they required was an incredible amount of hard coding. A human being would sit down and say, okay, we've got a black and white picture of whatever it is that we're driving through. At the beginning, of course, with RC cars or something very small or something like that, not real cars, but it graduated to real cars. But basically, you would look at images and you would figure out how to run a convolutional filter on them or something. This is not artificial intelligence, convolutional neural networks, but it's the same basic idea. It's just done by humans. But you would run this, you would look for edges, you would look for edges that matched up into some sort of format. It's really, really complicated. Anyway, and eventually you would stitch together something that looked like a curb or another car or some sort of object. And then your toy car or your real car could drive through that scene. And it could do it very, very slowly, usually under a mile an hour or something. And it would hesitate a lot. And if anything was weird, or if the sun angle was different or something, it would break. So very, very fragile stuff. And this actually goes for the decision-making process and the control output as well. So I'm not going to dwell on that too much when I get to it. But back in the day, all of this stuff was hard-coded, and it was heuristics by a human being deciding what the input space should tell the vehicle in terms of vision. And remember, we weren't only looking at vision, we were looking at radar, we were looking at LiDAR, we were looking at ultrasonic sensors, et cetera, et cetera. But overall, the basic goal was to take all of that input in, process it to the best of your ability, run it through some filters and things like that, and see if it matched up with something a human being had coded before. And if it did, then you would be able to pass it down to the navigation decision-making process. Then, of course, that navigation decision-making process was a bunch of heuristics that a human being coded as well. So they would make decisions like, if I see this, do this, right? So if you see like you're running into a curb or you're running into a mailbox or you're running into a garbage can or something, it's like, well, turn, get out of the way. So you would make a decision based on that. And so you'd have a bunch of heuristics like, if I see this, then do this. If I see this, then do this. If I see this, then do this. And so you would do things, but of course you're going to get very robotic driving. And then output controls are, if the decision is turn left, well, how far do I have to turn the wheel that much? Then you would have to do some integration and stuff so that the wheel wasn't going like that constantly. Because remember, if this thing's running at say 12 or 15 or 20 frames per second, it could be making a different decision every single frame, which means that, and I'm sure people can remember this from, early experiments. If you look at old videos and stuff, you'll see the steering wheel and everything in the car being very, very jerky. But basically you use an integration so that you integrate over time to try to smooth out all of those little bumps and get kind of an average decision-making process over time to make the car drive relatively smoothly. So that's the way that you do it with heuristics. The deal with an end-to-end neural network is that you're taking all of the decision-making process out of a human being's hands. In other words, type. You type in the heuristics and you're saying, if you see these tiny little features, maybe it adds up to this. Hey, look at some other little features, maybe it adds up to this, etc. And then you get to the control decision process and it's like, well, now what do I do? Then you get to the output process and it's like, well, given the decision that I've made, how do I actually turn the wheel, press the accelerator or press the brake? And what you're doing is turning from all of that human hard-coded stuff, that would be software 1.0, as Andrej Karpathy talked about, to making a neural network. So we can just imagine it for today as one monolithic neural network. I do not believe that this is how Tesla is doing it, just because it's so complicated to make that all work as one gigantic network for something this complicated. I think that more than likely what they've got at the very least is one for vision, one for the control decision-making process, and then one for output. And they've stitched them together, which is the reason that Elon in tweets has said 99% plus neural network code. Because I think they've got like stitching of traditional code to like pass things from one of these modules to another. Now, it could be way more complicated than that. We have definitely seen previously how the vision system used what Andrej Karpathy called a hydronet. And I think that was even after he left. Ashok and other people have talked about that as well. They may not be doing that anymore, but that was like a gigantic trunk, and then it had a whole bunch of inputs and a whole bunch of outputs that came out of it. So something like that is highly probable. I think they're probably doing something like that because, again, it makes the training so much easier if you can pull out individual pieces, but they might be going with something much more monolithic, and so it might just be one giant input space right now, just for the vision and detection modality of the vehicle. But anyway, today we're just going to assume a gigantic monolithic thing, which takes photons in at one end, and at the other end, it actually turns the wheel, presses the accelerator or the brake. And remember, this works for Optimus too, where the output space is much more complicated because it's moving around a body as opposed to just 3 output controls. So, okay, the vision in system, you've got a neural network rather than human coded stuff. So what you need to do is you need to build a neural network architecture. You need to build a neural network that can understand this. That is not a trivial thing to do. Tesla has been working for years to build that architecture, and we've had bird's eye view networks or BevNets. We've had occupancy networks. We've had the language of lanes. We've definitely explicitly seen that. And previous to that, we saw raster images where they would take each individual image, take the raster of it, and figure things out one frame at a time. There's been a lot of stuff that's happened over the past 7 or 8 years as Tesla's been working on this. So there's been a bunch of different iterations of this. Again, super, super complicated metaphor of being in the woods at night in the dark. You're bumping into trees. You don't know where you're going until you actually get out of the forest. So that's the situation that Tesla's been in. So, no knock on them that they've tried a bunch of what might turn out to be dead ends, or they could be things that you can utilize on the back end for data to make things work better. But anyway, in terms of the actual neural network, they're probably not being used anymore as of version 12. So once you've got this architecture, the big deal is you can no longer tell it what to do. In other words, you can't have a human being say, if you see a stop sign, then stop. And this is something that Elon and Ashok actually mentioned in their drive. 0.5% of people, NHTSA needs to fix this problem, will actually come to a stop at a stop sign, a complete stop. stop. So it's very difficult to pull the data out of the fleet to actually do that. And my contention is that those drivers are bad drivers because good drivers don't actually stop at stop signs. They just roll through unless there are other cars around, obviously. But anyway, what you can hear from this conversation is that Tesla is no longer able to tell the car what to do. So in terms of the vision space, what you do is you build the architecture for that part of your neural network to whatever it needs to be, something, some giant block of code that's actually a bunch of tensors, which is multidimensional matrices. It's taking numbers in from the input space. In other words, the cameras send it raw photons. So the photons come into the input space of this neural network. The neural network just multiplies and adds a whole bunch of weights. And as it's training, it actually keeps changing those weights. Of course, in your vehicle, it does not do that anymore. It's just doing inference. It's not training anymore. But in the training scenario, it actually does this and makes a prediction. And when it's wrong, because you can tell it whether it's wrong or not, you then pass the mistake back through the network and it adjusts all of those weights to make them a little bit closer. And if you do this with millions or hundreds of millions or billions of videos, you eventually train this network that under all circumstances, pretty much just like a human being, it will understand what everything is in the space. You have no longer explicitly said this is a stop sign. In fact, the car doesn't even know the concept of a stop sign. It just knows the concept of video input. It's like video input. I see this thing, which we would call a red octagon with a white outline around it with the word stop or whatever it is in your language written on top of that. And we interpret that as a stop sign. And we have kind of a semantic understanding of stop. Stop is also in English. So we're like, yeah, we understand what stop means in English. So it makes perfect sense to us. So you don't get that with the car. The car is learning that, but it's learning it in a space that's non-linguistic. So it's actually having to come up with its own version of semantics. It's got something really interesting. In fact, I hope someday somebody can break this apart and do a research project on what the semantics underlying full self-driving version 12 are, because it's had to create its own, because basically we've just said, here's a bunch of videos, watch it. And remember, we've also got IMU data. So not only do we have videos from people driving cars, we also have the acceleration profile, the, how hard you're turning profile, all of that stuff does get mixed in as well. But again, for today's discussion, we can kind of ignore that, but that is part of the process because you also don't want the car completely jerking, like coming up to the stop sign and just going really, really fast, jerking to a stop and then taking off like a bat out of hell. So you want to make sure that you do all this stuff smoothly as well. So you do need to take account of that IMU data as well, at least as far as I know. I mean, maybe it actually can just look at the pixels of a video and go like, oh, I see the person is slowing down like 10 seconds before the stop sign and, coming to a complete stop or something. I don't know. So maybe they don't even need that anymore, but I think that they probably do. But that's a different input stream and it can be done secondarily, but it's a good idea to have that in there to make sure that the car not only drives properly, but also drives smoothly. So again, we don't have a programmer explicitly anymore telling the car what it's seeing or how to see that object. We're just throwing hundreds of millions to billions of miles of data at this car, and we're just showing it the videos and it's figuring it out on its own. And when you hear about software 1.0 versus software 2.0, that is exactly it. Software 1.0 is a coder, a traditional coder, writing in exactly what the computer is supposed to do. And hey, guess what? You get exactly out of that what you expect, which is you get a robot. You get the car doing exactly what it's told what to do. And if it doesn't see that, it also will crash and stop. So you'll end up with like Cruise or Waymo or something where the vehicles will actually just stop on the road because they don't know what to do anymore. The whole point of what Tesla is trying to do is to get away from that robotic behavior, the brittleness of it, where it can break very easily. If it sees, inevitably, it's going to see a case that it's never seen before because reality is super messy. And so what you've got to do is you've got to be able to create a robust enough network that it's able to just detect everything, and it can be kind of fuzzy. It's like, I've never seen anything exactly like this before, but I've seen something really, really close to it. And because of that knowledge, I'm like, okay, I'll drive in as close an approximation to what I've seen before as is possible. And that's the same way a human does. If you drive, for example, in a different state or a different country or really weird weather that you've never been in or something like that, you figure it out. You use your past experience to sort of go like, okay, I've never done this before, but I've done similar things. So I'm going to drive in a manner that is similar to that, probably a little bit more conservative, which is one of the big things that people have against full self-driving, is it tends to be rather conservative in terms of its decision-making process. But a lot of that I chalk up to the fact that it's still learning. It's still kind of like a baby driver. And so it's just not that confident about what's going on yet. So that's our vision in. We just take in raw photons and we interpret it. And we don't know how the black box is interpreting it at this point. We've just got a world model that it's built up on its own. We've got a semantics that it's built up on its own. It has nothing to do with English or anything that human beings understand. It's just made that on its own. Now it gets to the central block of this whole thing, which is the decision-making process. And that is a process. There are two pieces to this puzzle. One is short-term, which is don't crash into stuff. And two is navigation. How do you get to where you're going in the most efficient manner possible? So again, in this step, we're moving from heuristics, from a coder saying exactly how to do all of these things, to the computer figuring it out itself from lots and lots and lots of data. And from what I understand Tesla did, they moved the vision part of things, the interpretation, the understanding. That's the first thing they moved to neural networks because that was the most difficult thing to deal with. It was very hard for them to deal with that, to make sense out of the world, and everything else downstream is predicated on that. So it was the hardest task, and it was also the one that everything else depended on. So they did that, and they've been working on that for years. You've seen research talks and you've seen AI Day 1 and 2 and all of that, where they really get into that, and they've mostly focused on the vision. And then the next step after that was to move to the decision-making process and say, okay, how do we decide what to do next based on this vision? And again, here, moving from software 1.0 to 2.0, we move from heuristics, where a person has typed in, if you see this, then do this. If you see this, then do this. I'm thinking of Kermit the Frog going like this, you know, the meme. Anyway, all of those kinds of things that a human being has to put in. And again, you just can't come up with every single possibility or eventuality. And so therefore, the better solution is to go with a software 2.0 type of solution, which is just to give it a neural network architecture, give it some stuff that comes in. This is what I'm seeing. And then output is, this is what should happen when you see this. In other words, what you pass down to the control output section of the neural network. So like I said, there's two pieces to this puzzle and they actually conflict with each other. The short-term one I think is actually very good at this point, and that is the don't crash into stuff. So it's like, you know, what's going on right now? Is there a car in front of me that's braking really hard? Do I need to make a turn because I can see the curb coming up, and so I need to, you know, follow the line of the road and make sure I don't get out of my lane? Do I need to stay in my lane? Do I need to adjust slightly to stay dead center in the lane? Whatever those kinds of decisions are on a very, very short-term basis, it does a really good job with. The problem that I continuously have, and I see many, many other people have with full self-driving, is the integration of navigation. And I think it's just a complicated problem. If you think about the entire structure of this end-to-end neural network, it's like take photons in, figure out what that is, make a decision based on that, and output the control. The navigation has nothing to do with that. What you're doing is essentially plugging the navigation into the middle of this process. And by doing so, you're introducing a variable that's really not part of the original neural network process. And I think it's that integration that causes the problems. So basically the integration right now is you've got Google Maps and that transmits it to Tesla, and then you get a decision about what your route is or something. So let's say you've got to move over from your lane to a lane to the right and then make a right-hand turn. Those are decisions based on the navigation information, but the way that that gets passed into the neural network is very different. You can't watch a video to see how to do that, if that makes sense, right? All of this other stuff, if you imagine, I'm thinking of A Clockwork Orange where, oh gosh, what's his name? I can't remember who the actor was. Anyway, but that scene where they're retraining him and they prop his eyes open and just make him watch all the ultra violence and everything. I think that you've got a similar situation with the full self-driving, right? You're just metaphorically propping its eyelids open and just feeding it hundreds of millions of miles worth of information and curated information. That's very, very important. Really, really good drivers doing a really, really good job. And it's saying like, okay, I see this, I see this, I see this, I see this. And then it starts making virtual decisions. So it's actually outputting what it would do. And then it can check versus what the human did. And in that case, it's like, oh, I did it right or I did it wrong. And if it did it wrong, it goes backwards and it figures out and adjusts all the weights a little bit. And over time, it figures out how to do that. But the question is, how do you integrate navigation information into that process? It's really not an easy thing if you think about that, because this is a completely separate control that's being sort of input from the outside. It's like a Deus ex machina sort of thing that's like, hey, you need to go over here, so figure that out. And so that's just being added to this whole thing that has nothing to do with the videos that you're seeing, unless they are able to actually take the map data. So let's say they can actually grab not only my video and all of that input, but also where I'm headed. And this might lead to privacy issues, which might be making it difficult for Tesla to do this. But assuming that we don't have to deal with that, they could also feed in the navigation information, which is like, right now you're here and you need to go here and we need to get into the right lane and then make a right-hand turn. And if you can do that integrated in and time synced up with the video, then maybe you could train it the traditional way. But aside from that, I just don't know how you do that. It's very complicated. The only thing that could happen is that you get a whole external little stack, a blob up here that goes like, right now you need to get into the right lane. And that's difficult because, again, it's kind of like heuristic code. It's very brittle. It's like right now is a very squishy thing. If you think about being in busy traffic and having to move over a lane, you kind of keep an eye out on who's doing what in front of you, who's doing what behind you, and when is a good opportunity to get in there, and also how far up ahead it is that you need to actually make that turn. So there's a lot of decision-making process that happens at this point, and it's kind of fuzzy, and you need to be a little bit loose about that. And so you really don't want you've got 0.3 miles, get into the right lane now sort of decision just being plopped on top of this. And again, my contention here is that that's the reason why the navigation is such an Achilles heel for full self-driving. Now, I don't know how it's been integrated into full self-driving version 12, but even 11.4.7, it's still not ideal. The car has a difficult time dealing with that. But I think that's the main reason why it has a problem, is because it just doesn't fit with the rest of the pipeline. So maybe Tesla has figured this out and they figured out a way to input the map data directly into it as it's training and made it figure out how to do that and to back propagate all of this stuff. But that's a fairly complicated thing to do. So anyway, I don't know what they've done and I don't know how they're going to solve this problem. But when people get mad about the fact that it navigates poorly and it doesn't integrate it, that's the reason why it's really, really difficult to integrate this navigation information into the photons in to control out neural network structure. All right, so that's complicated, but at some point you get an output of all of this stuff and it says, okay, the next thing you need to do is do this. And then it passes it down to the last module of the neural network architecture, which is, what do I actually do? How much do I turn the steering wheel in the next 1/36th of a second? Because it's making a decision every 1/36th of a second, as Elon said. And how much do I press the accelerator? How much do I press the brake? And again, you need to integrate this stuff over time. You don't want it every 1/36th of a second making an independent decision. And again, all of this code, and I believe even in 11.4.7, this part of the code is still heuristic code. It's very much based on human software 1.0 coding. And that's one of the really big differences between 11. Whatever and 12, is that they've also moved this part over to the neural network stack. And the way you do that is just like everything else, given all these input controls in the video I'm watching, what happens next? And the computer makes a prediction as it's in training, and then it sees what actually happens, and it's like, whoops, I made a mistake, and then it has to back propagate all of that stuff and fix it. And so over time, it keeps adjusting the weights, and it finally gets the weights right until it actually makes a good decision. And that's going to lead to proper driving. It's going to lead to smoothness. Smoothness is a really big deal. When you move from bleeding edge beta testers that are like, I don't care if it's smooth or not, it's driving, it's really cool, and I'm enjoying this, to the standard driver who is like, I don't care how this works, I just don't want it going like, jerking and making me car sick and making me worried that the car doesn't know what it's doing. I want that confidence. I want that smoothness, just like a professional driver. I want somebody who's really good. And so again, you can train it up on this just by taking the outputs of everything else and the video input and saying like, what would your decision be? It makes a decision, it's wrong, it figures out what the problems are, and it does a slightly better job next time it makes that prediction. So that's what we've got going on. We've got photons coming in, we've got neural networks deciding what is this world, and that's the semantic aspect. Then we've got a neural network saying, now what do I do next, with a weird plugin from the navigation information that's coming in kind of from the outside. But anyway, it makes a decision at some point and then it passes it down to the module, which is, okay, what do I actually do? And that decision-making process leads to the physical controls of turning the wheel or accelerator or brake. And again, with Optimus, all of the stuff is the same, except of course the training data is different because it's in a building or other things like that. But the output control aspect of it is way more complicated. So heuristically, you can get away with, a driving machine. It's not that difficult. There's only 3 degrees of freedom, the wheel and the accelerator and the brake. So it's pretty easy to do that with heuristic code. And that's the reason why this is the last thing that's been replaced in the cars. With Optimus, not the case at all. If you don't have a neural network architecture running the output control, it will like move like a robot, fall over, do all sorts of crazy things. So in my mind, what they did was they actually probably first built this output control neural network architecture for Optimus, and then they moved that, they kind of plugged it into version 12 of the car. That would be my guesstimation as to how that all worked. Or of course, they could have done the work in parallel. But anyway, I'm sure that Optimus was inspiration for a lot of how the output control neural network architecture should look. All right, so that's the big picture of how perception and planning and output all work together in a human being, in traditional full self-driving cars, and in the new full self-driving 12. Obviously, I have left out a lot of the details, but again, I wanted to keep this fairly high level, and it's already going to be 20 minutes plus. So, I think it's long enough already as it is. If you have questions about this, if you're like, wait, how does this work, or how does this work, or anything like that, please do let me know in the comments, because of course I can do follow-up videos. And like I said, I want to do one that's more in depth about diffusion models versus convolutional neural networks versus transformers. So we'll get into the weeds a little bit more later on. So definitely stay tuned for that. And actually, while you're doing that, please do like the video and also consider subscribing so that you can see when this next video comes out and for more of this kind of content. As always, a huge shout out to my Patreon patrons, my YouTube channel members, and of course, my ex-subscribers. Thank you all so much for supporting the channel in any way that you can. And of course, if you want to join any of the teams, just check out the links in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have TeslaBot t-shirts, the Tesla meme t-shirt, success is a possible outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on and on. So check it out. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a new Tesla, a solar roof, a power wall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.